one is very different from the other. AirMod is a regulatory model, and I'm going to talk about what a regulatory model is. And R-Line is still a research model that's still being used to look at the impact of highways. So first, what is a model? So let's get that out of the way. So the first model is actually very, very simple. Frank Pascal published this paper in 1961. That's 40 years, over 60 years ago in 1961. And it was a very simple model which looked at dispersion from a point source. It's simply a mass balance. All you have to do is, if you notice, as the plume spreads from a surface release, so this is a surface release. So as the plume spreads, it goes vertically. It spreads vertically because of atmospheric turbulence. And if you look at the top view, it spreads horizontally. And what Frank Pascal did was the concentration was simply the emission rate divided by the wind speed, h times w, which is simply a mass balance. And what Pascal did in 1961 was he provided the variation of the vertical and the horizontal spread of the plume with downwind distance as a function of something called stability classes. And if you look at textbooks, even now, they still talk about stability classes, even though it was actually proposed in over 60 years ago. And I'm always surprised that they're still teaching what I think is not very useful stuff. And it's based on an experiment that was conducted in 1956. That's over 60 years ago. So, but this simple model is essentially a mass balance, and mass balances are used in almost all air quality models. Of course, there are complications associated with computing the wind speed, the vertical spread, and the horizontal spread, but this is the essence of a model for short-range dispersion. I am not going to talk about chemistry. I'm not going to talk about ozone and all the other stuff. I'm going to talk about pollutants that can be dispersed in the atmosphere, and I'm going to talk about models that are used over length scales of something like 50 kilometers at the most, maybe 10 kilometers at the most. So how are models used? The first thing, one thing I say is a model is a mathematical description of the system that governs air quality. And of course, once you've created a surrogate for the real system, you can conduct experiments in this surrogate, which is the mathematical model, that are not possible in the real world. For example, you can change emissions, you can change locations of sources, you can do all sorts of things. Once you have validated the model, you have to be convinced that the model is actually working, that it's a good representation of reality. In essence, a model is simply this equation, which basically says the observed concentration is the emission rate multiplied by something called the source receptor matrix here, plus a residual. So this is the measured concentration. So what you're trying to do is explain the measured concentration in terms of a predicted concentration. And your predicted concentration consists of the emission rate, the emissions. Of course, there are emissions models also. I'm not going to talk about emissions model. I'm going to simply talk about the source receptor matrix that depends on metrology. It depends on a whole bunch of variables that determine how the material is transported from the source to receptor. And what I want to emphasize is there's always a deviation between observations and model predictions. So this term is the model estimate, and this is the observed value, and this is the residual, which is basically the deviation, and this is usually fairly large. So what you do when you have a large deviation between model estimates and observations, and that's a big challenge in air pollution modeling. There's always a deviation. It's not, if you see a good correlation between observed and predictions, and it's a good line explaining everything, you should be suspicious of what's happening because the deviation is usually large. So how are models used? As I said, it's understand source receptor relationships, which is basically this equation, and then it's used to manage air quality. You control emissions, you change locations so that air pollution is mitigated. So that's one of the primary applications of air pollution models, is to understand source receptor relationships so that you can manage air quality. You can use models to actually interpolate between observations. For example, if you have 10 observations over, say, Chennai, you want to get estimates of the concentration between those observations. So use a model to actually fit the observations and then interpolate it. Another major application of a model is to permit new sources. That is, if you want to build something new, you have to go to the local air pollution control board and say, I'm going to emit so much. Can I emit so much? So they'll run it through a model. I don't know which model they used in Chennai, but in the US, they use AirMod for point sources. And this is a legal issue. This is a legal issue. So in order to permit new sources, you have to have a model that everyone agrees with. That is, industry, for example, will object very much if they don't like the model. If the model predicts very high concentrations, they don't like it at all. So there's usually a long process before industry actually accepts it. So I'm going to talk now about the steps that are used to construct a model. First is, what are the characteristics of these models? First of all, in order for a model to be acceptable, the formulation of the governing physical processes ideally should be transparent. That is, people looking at the model should say, well, I understand what's happening to some extent. Obviously, you're not going to understand the details, but it shouldn't be a black box where you say, well, you have inputs and outputs, and that's what you have to believe. Most people won't believe that. So you have to have a transparent formulation. And the second thing is it has to undergo extensive evaluation with measurements to convince yourself that the model is actually mimicking reality to some extent. And then, of course, the third requirement, which is not always kept, is the computational requirement should not overwhelm users of the model. It shouldn't be so complex and so computationally cumbersome that people cannot use it. So these are the ideal requirements of a good dispersion model or a good air quality model. So what are the steps involved? So once you have decided this is the type of model you want, you have several steps. First of all, you have to motivate the need. And then you're assembling a project team that actually can come up with a model. It's not a one-man or one-woman operation. Coming up with a model is a fairly resource-intensive project. And as I'll show you, it involves a lot of people with a lot of skills. And then once you assemble the project, you have to formulate the model components. You have to write the equations down, and then translate these formulations into code. And that's not always easy because the person who's coding might not be the same person who's formulating the model. Then you have to test the code, make sure it's working. Then, of course, it has to go through evaluation with measurements or observations. And then, of course, this is an iterative process. You modify the model, then go back, modify the model, then again evaluate it with measurements, again modify. So this is an iterative process. These two tests, of course, you have to test the code throughout the process because quite often there are big errors in the code. And we are still finding, by the way, you'd be surprised, we are still finding errors in AirMod. And we are still changing the code because these are errors. People don't notice these errors, but we do. People who are actually looking at AirMod do notice it. In order for you to get to a regulatory model, there are stricter requirements. You have to publish the results in a peer-reviewed journal, and people have to accept it. Then you have to propose the model to the public. And then the public has got a comment period where they essentially spend 3 to 4 months commenting on the model. They send it to their own consultant. The consultants come back and say, well, this formulation is not right. I don't like this. It's predicting very high concentrations. So there is a back and forth process with the Air Pollution Control Board, or in this case, the US EPA. And finally, it is promulgated. So what did AirMod go through? So I'm going to give you a test case. The first thing that happened, what motivated the AirMod? In the 1970s and 1980s, there were major advances in micrometrology as applied to air pollution. Before that, it was Pascal. People were still using stability classes and dispersion curves. But during the 1970s and 1980s, we saw a rapid advance in how micrometrology was applied to air pollution modeling. In 1986, the American Meteorological Society organized a workshop. In fact, I organized the workshop on behalf of the American Meteorological Society in 1986 to discuss advances in dispersion. Myself and a person called Jeff Weil, we organized this. Then that workshop resulted in these lectures in air pollution modeling. Some of you might have seen it. I think it's out of print now. But this was published by the American Meteorological Society that summarized the lectures given by a lot of people like Gary Briggs, Jim Deardoff, Ian Sykes, John Wingard, some of the people who had made contributions to air pollution and dispersion. These lectures were published in 1988, at which point we said, okay, let's go to the US EPA and say, let's go ahead and change this Pascal-Gifford dispersion, ISC, people have used industrial source complex model that was still based on very old science, 60 years or 50 years old science. So we said, it's time we change things. So the US EPA held a workshop in 1995, and I mentioned Joe Tickwart because so many things in life happens because of good leadership. If the leadership is bad, things never happen. So Joe Tickwart was in the audience. He was the head of something called the Office of Air Quality Planning and Standards at the US EPA, and he bought it. I gave a talk, and so did Jeff Weil, and several people said, we need a new model. So he decided, okay, I'm going to fund this to the American Meteorological Society so that we come up with a new model to replace the industrial source complex model, which is still surprisingly still being used. It's based on Pascal-Gifford stability classes and dispersion curves proposed in 1961. And it is based on, by the way, it's all by even my standard. Of course, I'm ancient, but even by my standard, it was pretty old, 1961. And it is based on the prairie grass experiment, which was conducted in 1956. At which point we said, let's go ahead and do it. So we formed something called the AMS EPA Regulatory Model Improvement Committee. It was formed in 1991, and the chair was Jeff Weil from the National Center for Atmospheric Research, NCAR. Then it included a person called Bob Payne from a consulting company called Ensor Consulting. It no longer exists. It's actually bought over by another company. At that time, I was also working for a consulting company. So I was one of the people who was part of the committee. Then there were a whole bunch of people from US EPA, Stephen Perry, Al Cimarelli, Rob Wilson, Russ Lee, Warren Peters, and Roger Broad from a company called PES, Pacific Environmental Services. So the basic way we worked was all of us got together 2 or 3 times at US EPA, and we generated, as you can see in the picture, a lot of hot air. 3 days of we sat together and wrote equations down and discussed those equations. We had access to the library. So the basic concept was to formulate the model in a group. And surprisingly, there was very little disagreement among us. Most of the time we spent actually laughing and being good, nice to each other. Very few disagreements. There were very few people who insisted on certain things. So this group actually worked out extremely well, primarily because we worked well together. So one of the secrets to accomplishing anything is to actually have a good group that sort of has got good chemistry. Of course, at the end of the day, we went out and had dinner. We had fantastic dinners. And in fact, in the mornings, the first thing in the morning was to plan which restaurant we would go to that evening. So this would happen maybe 2 or 3 times a year, and during which time we would formulate the model and then give it to Roger Broad. Roger would then convert all these equations into code. And then he would come next morning and he would work through the night, come next morning and say, here is the code and this is what it's doing. And sometimes he would say, this is nonsense, it's not working. So this went on for some time. That's how the committee worked. And what did AirMod include? It included a new boundary layer module that created all the inputs for AirMod. It's called AirMet. Some people might be familiar with it. It computes boundary layer variables such as boundary layer height, surface friction velocity, Mononovo-Koff length, and all the variables that you need to do dispersion. And then we had a complex terrain module. Obviously, I can't go into the details. You can actually look up the book. This paper here is published in the Journal of Applied Meteorology in 2005. That was long ago, 17 years ago. But it's still one of the most widely cited papers because people are still discovering it. So we included, like I just gave you some equations I cut and paste from the paper. We actually had boundary layer variables to compute the wind speed as a function of height. Then we use boundary layer variables to look at the vertical spread and the horizontal spread. So here is a sort of examples of the type of variables that were included in AirMod. And some of you might already be aware of it. But the main thing I wanted to emphasize here is that we tried to make it as scientific as possible. And we used a certain approach. Here, it's not changing. Let me see. Okay. So what was the basic approach we used in formulating? And this was a very important thing. when we formulated the model, we used a certain approach. We said, let's formulate the model to satisfy theory at two extremes. For example, neutral and very stable, neutral and very unstable. And then we patched in the formulation between the two limits using a parameter. For example, complex terrain. A plume can either go over the hill or hit the hill. Under very stable conditions, the plume can actually hit the hill, or in other conditions, it can go over the hill. So what we said was, let's go ahead and construct a plume model that goes between the two limits. Similarly, under low wind speeds, the plume can go all over the place, correct? It can spread all over the place, or it can behave like a plume. So we said at intermediate wind speeds, it can either behave like a random pancake, that is like a dosa, let's call it a dosa, all over the place, or it can behave like a plume. So at wind speeds, intermediate wind speeds, we said, okay, let's interpolate between the random plume, as we called it, and the plume, and the actual plume. So this was the approach we used in model formulation. The advantage of this was we knew that the model was working in the limits. So anything we put in between was between the two limits that we knew was right. So this was the basic approach to model formulation. And this basically is the theme you'll see in entire AirMod, interpolating between limits. Okay. And of course, what I'd like to point out is that we used a lot of databases to evaluate the model. So there was something like 17 databases that were used to evaluate the model. And here is an example. I don't want to obviously go through the details of this, but the point I want to make is it went through extensive evaluation. But what does model evaluation mean in air pollution modeling? It means a very different thing. And as I insisted, and I told you before, that the deviation between model estimates and observations are fairly large, which means that if you do a scatter plot, it doesn't look very good. So one of the things we did was we compared distributions of measured and model concentrations. We didn't do a one-to-one correspondence. So these are basically ranked observations and ranked predictions. So you basically what you do is you rank them from lowest to highest concentrations observed and lowest to highest predicted concentrations and plotted them. So what you see here is actually not scatter plots, but distribution. So you notice that we had to show that the new model performed better than ISC. So there was no reason to actually throw out ISC if the new model didn't work better than ISC. So here you see that we had to actually publish results, show to the whole world that the new model actually worked better than ISC. So here is a plot of distribution. So you see here again and again that AirMod actually performs better than, except for prairie grass. And the reason ISC did well for prairie grass is that, of course, ISC was developed with data from prairie grass data. So the point I was trying to make here is the deviations between model and corresponding measurements are usually large in air pollution modeling. That's something you cannot avoid. In most cases, you're happy when the distributions are similar. That is, the highest concentrations are predicted correctly, the lowest concentrations are predicted correctly, and that's all you can be satisfied with. Of course, in certain cases, you can get good correlation, but in most cases, you have to be happy with distributions. So let me see. Okay, here is the timeline, and this is going to shock you. So we started the project in 1991. 14 years later, it was promulgated to replace ISC. And the reason, of course, is because it's a regulatory model. Regulatory models have a lot of inertia. It has to be accepted by the entire community. It's a legal matter. It's actually part of the Federal Register. It's part of the law. It's part of the federal law. So if you see the model, AirMod is actually published as part of the law. So it took 14 years to come from 1995, and by the time I finished it, I was an old man. I started in 1991 when I was pretty young, and by the time we finished it, I was an old man. So this is basically what AirMod took 14 years to develop, and people are using it all over the world, and we're still improving it. So I'm going to very quickly go to a next case study, which is modeling the impact of highways. And let me see what the time looks like before I go. Okay, I do have time. So, the next thing I'm going to talk about is modeling the impact of highways. Highways are the major source of air pollution. I'm sure in in Chennai, in Bangalore. My hometown is Bengaluru, as they call it. Highways and roads are the major source of air pollution. So here also in the United States, power plants and other point sources are no longer big sources. So we spent some time looking at modeling the impact of highways. I was fortunate enough to be involved in it right from the beginning. So the processes that govern a highway dispersion is fairly simple. First of all, you got emissions from cars. And by the way, this is what I drew. So if it doesn't look very good, you have to blame me for my lack of artistry. So you got turbulence spreading the plume. Initially, over the highway, the concentration increases over the highway. And then away from the highway, it decreases. And what determines it? It depends on the traffic flow rate. It depends on the emission factor. It depends on the width of the road. It depends on turbulence. Sigma W is the turbulence, and of course the distance from the road. It depends on the wind speed. So this essentially summarizes some of the variables that determine concentrations from a highway. And it turns out that this rather simple model actually explains observations fairly well, which is rather surprising. In fact, I'll show you later on how it explains. So again, it depends on turbulence, which is sigma W is the vertical velocity fluctuations, W is the width of the road, E is the emission factor, T is the traffic flow rate, that is how many vehicles per hour, and this works fairly well for highways. But highway dispersion has been studied for a long, long time. And let me see, I got something, okay. Highway dispersion has been studied for a long time. It started off in 1970s, actually. There was the EPA highway model. And then some of you might have heard of the CALINE model in 1989. And then the R-line, of course, is in 2013. And then the C-line model. But the point here I'm trying to make is highway dispersion has been studied for a long, long time, but it's become very important nowadays because that's the primary source of air pollution now, highways. So, and we published a lot of papers. By the way, this is all the papers that my group published on this. And the reason I'm putting this up is to say that in order to come up with a model that's accepted by everyone, you have to actually convince the community that what you're coming up with is actually realistic. So we published a lot of papers, and so this sort of gives you a partial list. But one of the things I wanted to point out is that in order for the model to be accepted, you have to rely on data. That's an extremely important component of all modeling. If you do not have data, you do not have a model. So there is this constant iterative interaction between model estimates and observations. So one of the best sources of data are wind tunnels. Here you see the US EPA wind tunnel, and here you see a simulated freeway, and you see a simulated freeway, and here are the roughness elements, and these roughness elements actually create turbulence. So you have to simulate atmospheric turbulence. So I'm showing a part of the US EPA wind tunnel, but a lot of our data came from the wind tunnel in developing this model. And of course, in addition to the wind tunnel, they'll always tell you wind tunnels cannot account for stability effects because they're always neutral. You cannot shine the sun inside the wind tunnel. You cannot make it stable in the wind tunnel. So in addition to that, you have to have field studies. So here is a field study that was conducted in Idaho Falls in order to study dispersion from freeways. So the nice thing about this study was sulfur hexafluoride, which is a tracer, was simultaneously released from two line sources, one behind a barrier. And I'll tell you why a barrier is important, because a lot of the highways in the United States have barriers next to them. So they wanted to find out what happened to a barrier. So the barrier was constructed with hay bales, and it was 6 meters high. So these SF6 was simultaneously released from two sources, and the concentrations were measured at 56 receptors at both of these line sources, and it spanned neutral conditions. Neutral is basically high wind conditions. Unstable conditions is very sunny conditions on a very hot sunny day, and stable conditions during the night. So it spanned all the conditions, and this is one of the best sources of data to look at highway dispersion, which is essentially looking at tracer releases behind this. And this resulted in different formulation for the horizontal and vertical spread. And the reason I'm actually putting up these two equations is that these equations are expressed in terms of micrometeorological variables like friction velocity. U star is the friction velocity. And again, if you want to do air pollution modeling, you better learn micrometeorology. I keep on saying, so the first thing I do when I teach air pollution modeling is that I spend a lot of time on micrometeorology because most of the modern dispersion models have got a lot of micrometeorology built in, so you lose a lot if you don't learn micrometeorology. And hopefully one of these days, Shiva, we're going to have some courses in micrometeorology at IIT Madras. So here are two for stable conditions and unstable conditions. We got horizontal and vertical spread. As I said, most of air pollution modeling consists of computing the horizontal spread of the pollution and the vertical spread of the pollution and then the horizontal spread. And these explain the data very well. We had to convince ourselves that it explained the data. So on the x-axis, you see the model estimates and the measured sigma y. And this is excellent. By the way, this is the reason you have such fantastic comparison is because this was a tracer study, extremely well-controlled experiment, and you can get very good comparison only if it's a wind tunnel or a tracer study. Those are the two cases where the comparison between model estimates and observations are really good. So here we compared the horizontal spread, and here we compared the concentrations. Again, concentrations can be poor sometimes, but here is a comparison of the maximum concentration. And what you're seeing is a scatter plot of model estimates against observations. So these are under neutral conditions, very unstable. And these are factor of 2 lines. So if you're within a factor of 2 in air pollution, you're doing really good. And the correlation is extremely high. So we felt pretty good about coming up with a model that explains wind tunnel data, and it also explains tracer studies. And we also did a comparison with another model called the ADMS model, which the UK, the British put together. They competed with us, and finally they decided they lost. Of course, I'm kidding here. So here was our model versus ADMS. Actually, it does as well as ours, except ours is slightly better. But they also use micrometeorology. They also came up with, but I think our model is better. By the way, they tried to sell ADMS to the US. Of course, we have the not invented here syndrome. That is, if it is not invented in the US, people never accept it. So our line was accepted, and that became the model. So we also tested to some extent in the real world. The comparison was not that good. There was an experiment, a tracer study done in Sacramento in a real highway, and the comparison was reasonable, but not as good as. But again, you see the factor of 2. It is well within a factor of. Again, to students, what I want to emphasize here is, in order for a model to work, it has to compare with observation. You cannot construct a model without having good observations. So I'm going to go back to this field study, and now I'm going to look about the impact of barriers, and that's become an important issue because most highways in the U.S. have got these barriers next to the freeway because they want to reduce the noise from the freeway. They're essentially noise barriers. They reduce noise from the highway, but they also do mitigation. So that's one of the reasons we did this experiment to look at the effect of barriers. And barriers have a substantial effect on concentrations. So notice under neutral conditions, there's something like 40 to 60% reduction in concentrations next to the barrier. So with the barrier is the red, and without the barrier is the black. And what you see is the huge reductions in concentration, both under neutral conditions, under unstable conditions, and this is slightly stable conditions. And these are experimental values. So the basic message was that maybe barriers have got a mitigating effect. So a lot of agencies said, we want to take credit for barriers. So whenever there's a barrier, we are going to say the concentration next to the barrier is going to be lower. And the reason barriers are important is because a lot of people live on the other side of the barrier. For example, if you've been to Los Angeles, there are houses just next to the barrier. So we had to come up with a model to look at the impact of the barrier. So again, we went to the wind tunnel. and they could simulate all these different model configurations with elevated highways, depressed highways, barriers, upwind barriers, low wind barriers. So what you see are a flat one. This is flat, and this is an elevated highway. This is a depressed highway, and a lot of highways in the US that are depressed. They're well below the road surface. And then, of course, there are angles. And then sometimes they've got an upwind barrier, and here is a downwind barrier. So people live on this side. And then there are two barriers. So they looked at all these configurations, and we had to come up with a model that explains some of these configurations. So what does a downwind barrier do? It in fact lofts the plume, lofts the flow above the barrier. So here you see what a wind tunnel can do, which you can never do in the field. You can actually measure the velocity profiles using a velocimetry. You essentially release particles, and you can actually use a laser to trace these particles. So you can actually look at the velocity profiles, and you can look at the concentration profiles, which is just wonderful if you have a wind tunnel. Here you got ethane concentrations from different freeway, different lanes on the freeway. So you got 6 lanes on the freeway, and you see the concentrations below the barrier more or less flat, an increase in concentrations above the barrier. But you're worried about what happens below the barrier because that's where you live. So here you see these concentrations. You can see the evolution of the concentrations as a function of distance from the downwind barrier. And we actually came up with a model to explain the data. So that was one of our tasks, is to see whether we could come up with a model. And here you see a model that explains some of the data. My student and myself, Nico Schulte and myself, we came up with a model in 2014, which has been improved substantially to look at the effect of heights of barriers by Diana Francisco. This paper was published, I think, last week. This paper was published last week on the effect of barriers. So this paper is remarkable in the sense it looks at the effect of barrier on dispersion. It looks at 0 barrier height, then it looks at a 3 meter barrier height, a 4.5 barrier height, 6 meters and 9 meters. And here are the model estimates. I don't want to go into the details, but we could explain the data fairly well using a model. But what is rather remarkable is that all of this collapses using a rather simple model, which actually tells you what the effect of a barrier is. It turns out that the effect of the barrier is essentially pushing the road upwind. And we can actually calculate how far the road is pushed upwind using the barrier. So now you can see that this simple x naught is simply the barrier height divided by the turbulent intensity. So if it is stable conditions, the barrier is pushed backwards. So this is remarkable that all the concentrations more or less fall on the same curve using this rather simple model. And this paper just came out last week, as I said. So if you're interested in looking at the paper, you should see it. But we have been working on it from 2014. So this is basically more than 8 years later that we have come up with a model that explains. And research is still going on, by the way. Research is still going on this because we eventually want to explain it, put it into a dispersion model that can be used in regulation. So Caltrans, which is the California Transportation Agency, has funded a fairly large study with UCR on looking at the effect of a barrier in the real world. So this field study is described in a paper that just came out. So I'm going to go through this because I don't have too much time. I'm going to go through this but it was done next to UC Riverside. We released sulfur hexafluoride from 8 vehicles. So these 8 vehicles went back and forth on this. There was a barrier next to the freeway. And we had sonic anemometers that collected the meteorological data. And here's a sampler that automatically collected 6 samples an hour, or 5 or 6 samples automatically, and then it was analyzed in a lab. So this is a fairly major study that looked at the effect of barriers. And the question you need to ask is, if you've already validated it with wind tunnel and field studies, why do you want to do an actual field study? The reason is nobody in industry will believe all this unless you do it in the real world. So that's the reason this study was being done. So the reason I showed you all this was a fairly important study. that we just finished, and we have come up with a model that explains the data. I don't want to go into the details of the model, but it explains the data fairly well. Of course, there are discrepancies on some days, which, of course, the paper describes the discrepancy. Of course, the models don't always work well, but what you're seeing here is a half-hour averages, and it's working fairly well. So since I don't have too much time, I'm going to have some concluding remarks. Modeling is already a collaborative effort. You cannot create, one person cannot create a model. It requires significant resources. It needs a lot of skills, especially if you're coming up with models that explains photochemistry, aerosol chemistry, cloud physics. In fact, the acid deposition model that I was first involved in involved something like 20 people. It involved chemists, it involved cloud physicists, it involved numerical people. So it's usually a collaborative effort, and it requires a lot of resources, and it's a long process. Usually, you have to talk in terms of 5 to 10 years to come up with a brand new model, and requires an iterative interaction between theory and experiment. Again, I said experiment is extremely important. And then, of course, the third part is that it has to be followed up with resources to improve the model to reflect the state of the art. And this is not always done, by the way. In fact, US EPA is struggling with the third aspect, is how do we keep on improving AirMod, because people want to find mistakes with it. Fortunately, I'm actually involved in doing this. So I want to finally thank Caltrans, the California Department of Transportation, the US EPA, California Energy Commission, California Air Resources Board in the South Coast. I'm fortunate to live in a state, California, that is almost like a country on its own, and it funds a lot of research. It funds almost as much as US EPA, and they've got a lot of resources. In fact, even this year we got a surplus in California, so they're actually funding more research. That's it, Shiva. I don't have anything more, and I can take some questions.
Professor Venki, thank you very much. It is indeed, it's a great pleasure and honor to listen to you, because you have worked extensively on the model. And in India, we also use, AirMod has been recognized as a regulatory model. And many times they ask, particularly the environmental impact assessment, that they wanted to make sure that they will either use ISEST3, which is a older version. Now they are adapting to whatever the simulations made from the AirMod. In fact, our group is also using the AirMod for simulating the air quality in 4 cities in Tamil Nadu, and probably we're going to use AirMod in another city in Karnataka. So probably we will be in touch with you regarding those studies. So I'll just ask, maybe students have some couple of questions. Please type your questions to Professor Venki using the chat box. And I think, Suvarna, can you also make Professor Prasad Modak as one of the co-hosts? So probably he can directly ask some questions. He can interact.
Yes, sir.
So there are one question in the area of ANN based models and hybrid models. How existing models such as AirMod or Orline can adapt? What changes you would like to have in the models to be more decisive? So this is a student from our group.
I'm sorry, I don't understand the question. Could you repeat the question, perhaps? And I'm not sure I understand it completely.
I think Professor Venki's point is, I think now there are more, emphasis on ANN models, hybrid models.
Correct.
So in that context, how
you mean when you say hybrid models? When you say hybrid models, you mean a hybrid between statistical and mechanistic models? Is that
yes,
what you're saying?
Yes.
Yeah, I think people are using it here also in the United States, primarily to look at prediction of air quality. That is tomorrow or a few hours from now, because statistical models are pretty good at predicting. And then, of course, you can have a mechanistic component. And people are doing it. But if you want to apply in a regulatory sense, obviously you cannot. You cannot apply those models, because you essentially want a model that has been tested with data and is mechanistic in some sense. But AirMod is not likely to have a hybrid mode. It could actually go into a hybrid model, but by itself, it's never going to be a hybrid model.
Okay.
And Orline. All of these are mechanistic models, that perhaps when we incorporate it into a hybrid model for prediction.
Yeah. Professor Venki, I'm just thinking in the same line, whether shall we look at it for particularly, as you rightly said in the beginning, for the any new sources to be, permitted in a particular area, or a particular activities can be allowed in that location. So maybe the regulatory models may be more useful. But do you think that these other statistical models like ANN and maybe kind of an hybrid model should be meant for warning purpose, like a forecasting purpose?
Yes, I agree with you completely. It's very good for forecasting because you can essentially use past observations to predict into the future with a statistical model. And of course, you have a mechanistic component which actually makes it more reliable to predict into the future. But for permitting, as you point out, permitting is an entirely different process where you essentially come up with a new source and say, well, I'm going to emit so many kilograms per second or grams per second of sulfur dioxide or something else. Can I put this industry here? And of course, in the US, as soon as you say that, you have to run it through AirMod and show it doesn't use up the increment that's allowed. For example, the background could be some level, and you're allowed only a certain increment above that. And if you go beyond that increment, they say, well, you're not allowed to do it. You have to reduce your emissions. And that has worked fairly well. And the reason industry is so worried about it is obviously they want a model that predicts lower concentrations. So whenever a model actually predicts higher concentrations, they're extremely worried. But you're right, hybrid models are extremely useful for prediction, and they're being used to look at in a predictive mode. But I don't think from a point of view of, and even air quality management, I think you prefer mechanistic models where you can look at what if type of things, where you build this big model and say, if I change the sources here, what happens to concentrations elsewhere? So I think that's slightly different. But even I tend to believe that for management, we should sort of rely primarily on mechanistic models. But for prediction, I think statistical models are extremely useful.
I completely agree with you, Professor Venki. Yeah, this is another question. Can the shape of the road barriers have an effect on concentration? For example, instead of barriers with a flat surface, if we can have a concave or convex shaped barriers, we'll have some influence in reducing.
You haven't tried, because most of the barriers here are straight. I mean, building a sort of concave barrier is more difficult. I mean, it's as it is, it's very expensive building a normal barrier. Very, very expensive. So yes, I think it might have an effect. In fact, I'm collaborating with someone in Mexico, and his simulations, his CFD model simulations indicate that if you have a concave barrier facing the road, it actually reduces concentrations more. So he's going to do some field studies. His collaborator from Mexico, and he's going to do some field studies to see whether that's indeed true. But you're right, it could have an effect. The shape could have. The reason we haven't looked at shapes is primarily because it's not practical to create barriers that have a particular shape. And most of the barriers, as I pointed out, are essentially noise barriers. They're designed to actually reduce noise next to the freeway.
Okay. Yeah, this is another question from my other colleague from our SIPA network, Professor Karyachat. If air mode is a steady state model, if we applied air mode in a complicated areas with a fluctuation of weather, do you have any idea if we employ this model air quality dispersion under such conditions?
No, air mode, he's right, absolutely right. Air mode is a steady state model. Yeah, it shouldn't be applied much beyond 10 kilometers, especially under low wind speeds, because under low wind speeds, you have a lot of things going on. In which case, they do have models like, CalPuff is a model that looks at a puff moving around. There are grid models, but then the grids have to be very, very small in order for you to do the computation. And there are Lagrangian particle models that essentially release particles. Of course, there are a whole bunch of models that are designed for unsteady conditions. But the purpose is, why are you doing it? The first question is, why do you want to deal with unsteady conditions? Are you managing air quality? Or are you looking at some physics? If you're managing air quality, I am not entirely convinced you need an unsteady model, because managing air quality consists of essentially making some high-level decisions, and saying, if I put a source here, what's the likelihood that I'm going to get high concentrations here? It's not necessary to get an unsteady model to look at that. Because what you're really interested in is the distribution of concentration. What are the high concentrations and what are the low concentrations? For example, I'm now working on a project with the Federal Aviation Administration looking at the impact of airports. And we have decided to go for a steady state model, even though airports obviously have unsteady situations. And then our colleagues in Germany, there are two groups actually working on the same project. They've gone for a Lagrangian unsteady state model. We are now going to compare our two models and say which model predicts a better distribution, not actually what happens in a particular hour, but what happens under unstable conditions, stable conditions. And to me, a steady state model under those circumstances gives you reasonable estimates of the distribution of concentrations. If that's what you're looking for, is distribution of concentrations. What does the cumulative frequency distribution look like? Rather than what happens in a particular hour. If you're diagnosing, for example, a high pollution incident, and you want to do it with unsteady model, of course, that's almost obvious. A high pollution incident happens when there's a high pressure region there and the wind speeds are very low, in which case even a Lagrangian model is going to have problems because all the particles are going to accumulate. And it's almost obvious why the high pollution. So I think these unsteady models are very useful if you're looking at the physics, underlying physics. But to look at air quality management or to look at regulations, I'm not convinced that you need an unsteady model.
Yes, there's an industrialist. You also know him, Dr. Mr. S.K. Gupta asked why we should use models that are to
I didn't get it, Shiva. I lost you. I'm losing you, Shiva. I didn't get what you said. The connection, I think, is well. Go ahead again. Repeat it because I lost the connection. I think there's something wrong with the connection.
of course, just question. It's from.
Okay, now try again. Okay.
Okay, this is a validation. Do you suggest the model need to be?
Maybe I can look at the chat. If you can type in the chat, it might be easier.
Professor Venki, can you hear me now?
Now I can hear you.
Okay, so there is a question related to models validation. Do you because the models were effective in predicting the concept because we are validating that model for a specific location. So in that context, do we need to validate for more scenarios so that the model will be more acceptable? So this is a question from industrialists.
No, I think it's a good question people often ask me. If the model has got underlying mechanistic framework, it's got the physics in it, the fact that it works here doesn't mean if it works at a certain location, there's absolutely no reason why it shouldn't work somewhere else, as long as you've got the correct physics. So that's one of the reasons you want a mechanistic model that has got the underlying physics. So it's not necessary to validate it at different locations as long as the physics doesn't change substantially. But it should account for a lot of the underlying physics. For example, we've got complex terrain. Another thing that's very important for air mod is the urban pollution. And because that during in urban areas, the boundary layer is rarely stable. It's mostly convective. That is mostly unstable. So we have in air mod, we are now creating a situation where if it is over an urban area, we make it unstable using some methods. So So the bottom line is, to answer your question, if the model is mechanistic, there's no reason to validate it at several locations as long as it's got the components, correct components.
Yeah. Okay. Thank you, Professor Venki. I'll just see whether Professor Prasad Modak is here, and you have met him. He is one of the renowned, engineer and also an economist. I can say from the point of he is bringing a lot of economic dimensions to the environmental management. Professor Modak, can you hear us?
I can hear you, Shiva. I just wanted to say a big hello to you.
Yeah, thanks, Professor Modak. Very good morning. Yeah, Professor Venki is here. Maybe
yeah, hello. I might have met you in one of the conferences on my visits to India.
Yes. But I just thought of taking this opportunity to request you if you could speak a bit about your work on the box models in the early days, and that I thought was very stimulating. The kind of work which you publish on the use of multi-box and box models. I thought that was something very practical for many people to get into modeling activities. So if you could maybe couple of minutes on your work on box models.
Yeah, I did that initially eons ago, and that was one of the first papers I think I wrote on box models, because a lot of people, Heinz Lettau was using box models. A lot of people were using box models. Steve Hanna was using box models. And I think they're useful in some sense, especially indoor air pollution. People use box models, a lot of box models. But for large urban areas, I think it's difficult to use box models. Even though it's easy to use and gives you concentrations, I'm not convinced the box models. In fact, if you notice, my paper actually is a critique of box models. In fact, I go and say box models are useful for certain things, they're not useful for another thing. And I remember Hank Tennekes. Tennekes is a very big name in air pollution modeling. And Hank Tennekes was the first person to actually use box models for air pollution. And I remember visiting him in Netherlands when I was very young. And I went up to Tennekes, and Tennekes said, "You're the person who said my box model was wrong." And of course, he was magnanimous enough. He was a very big name, so he was good enough to say, "Well, it applies to certain cases, but I think people might over apply it and say, but it gives you a reasonable approximation to certain things. For example, it's a nice mass balance model, but I'm not entirely sure for unsteady cases it's very useful. For steady cases, for example, if you were looking at air pollution from Chennai, if you did a simple box model and you had a boundary layer height, you could basically predict the highest concentrations on a certain day. But I think to look at unsteady, where you're doing time variation. In fact, I think in my paper I looked at stagnation episodes in Toronto long ago, and I came up with a way of looking at stagnation. But I haven't used box models except that I've done multi-grid models. We came up with the first acid deposition model in Canada. There was a big problem with acid deposition from Canada, from the Inco nickel plant. I don't know whether you've heard of the Inco nickel smelting. It used to generate 5 kilograms per second of sulfur dioxide, 5 kilograms, and it used to apparently damage forests in the United States. So I used to work in Canada. So we came up with this model to look at the effect of acid deposition. There we used a multi-grid model, which I think people are using in India also. They're using multi-grid models all over India. But a box model, coming back, gives you, I think, a first cut useful estimate. But if you want to go beyond that, especially under unsteady conditions, you might want to use other models.
Right, thank you. Yeah. So, Professor Venki, I remember what we did years ago, that we used a multi-box model for Mumbai, and then we ran an inverse source estimation algorithm.
Okay.
And we came up with the emission distribution using the monitored data. We had these 22 stations. So we use ATDL, and then those days, and then wrote a complex box algorithm to figure out what could be the emission grid distribution.
Correct.
To prioritize the hotspots. So the model was used essentially for a better air quality management, to get a focus.
Correct.
Which were the grids which were really influencing the urban air quality. And you'll also be surprised that same ideas, when we looked at the Thames estuary model, the multi-box model for the rivers, with
Correct.
exchange coefficients. So I was looking at that time, how can I use box models for variety of environmental modeling applications? And the rivers were another case, where we could use multi-box, multi-layered models as well.
Correct.
And that was very encouraging because, it gave, like you said, a first cut on what
Correct.
kind of concentrations we were looking at in the rivers as well as in the air sheds. And then we realized that many of the air quality management decisions were not so much linked to the resolution of the model. What we needed was a sense of the extent of the severity of the problem, because the interventions didn't change much, whether I
Correct.
use a complex model or a simple model. So the
Correct.
model
Correct.
parsimony for management, it was something which I thought I learned a lot by using this stuff. And then obviously you do apply models like Aeromod to get much more better sense. So
No,
that's
you're absolutely right, Professor Modak. I mean, the model parsimony is not appreciated as much as it should be,
yes,
especially for air quality management. And the application you talked about, where you use box models to estimate what the emissions are, to find out what the probable causes of high pollution events
yes,
are, I think it's an
yes,
excellent application. Excellent application, and I've used it myself, by the way. I've used it in management where I looked at the, doing invert, what they call now is, I think it's called inversion. I think it's called model inversion or something. I don't know the technical name. They give it fancy names for these simple processes. But anyway, estimating emissions using a model is now one of the, the most active area of research,
yes,
where we are actually using, for example, I'm now involved in a research project where we are looking at methane emissions from dairies.
right,
Dairies are one of the biggest sources of methane emissions from manure lagoons. I'm sure you have dairies in India also, these large dairies. And methane, is a greenhouse gas, very important
yes,
greenhouse gas.
yes,
So we have got a big contract from California to look, again, California is funding this because we are interested in climate change. And
right,
we are
right.
looking at methane emissions from dairy, from manure lagoons, and we're using this model in an inverse mode. We are trying to estimate emissions from the model. And the application you talked about, where you put boxes over Mumbai, or you said Mumbai, I think it's an excellent application. And you are absolutely right. Maybe the resolution doesn't matter all that much, and the
Yes,
complexity doesn't change your decision very much about
absolutely.
what
I
happens.
agree with you. Yeah. Thank you.
Uh,
Thank you, Professor.
Yeah, Professor Venki, thank you. Professor Modak, thank you very much. Professor Venki, before we can close, would you also comment on, because they see that now these days the green barriers, also being one of the initiative in order to address some of the environmental pollutions. So,
Correct.
as you rightly said, the barriers in the roadside is very well studied. From the industrial complexes, do you also suggest that they should have some kind of a green barrier on the,
It
some
depends on
kind of
whether
a
the
boundary which
barrier
will,
is porous. I'm not entirely
yes,
convinced that porous barriers work very well, even though we are getting a lot of people think that, for example, I think people in UK, what's his name? Not Ashok Kumar, Prasant Kumar, correct?
Mhm.
He has been suggesting that if you put a vegetative barrier, it reduces concentration substantially. I think it needs to be solid for it to work, because as soon as the stuff goes through it, I'm not convinced that there's enough time for deposition to occur. So
Okay.
my feeling is, if you do some calculations, you find that there's simply not enough time for deposition to be effective. So I think if you put a barrier, a vegetative barrier that's fairly dense, I'm sure that would work, because it's almost a solid barrier.
Okay.
Because you need
Yeah.
the stuff to go over the top of the barrier and disperse in the vertical.
Okay. Yeah. Thanks, Professor Venki. And it's a very great pleasure to listen to you. And I request Dr. Madhusudan to summarize the lecture and,
Yeah,
close
I
out
was
of.
in India 2 weeks ago. I was in Chennai 2 weeks
Professor
ago.
Venki, you should have just, let's know so that,
No,
we
I
could
had to
just.
visit my mother for 2 weeks because she was not doing well. So I went and visited. A very quick trip. I went to Bangalore and came back in 2 weeks. In fact, 12 days. I spent only 12 days in Bangalore. But I'm going to come in summer, during which time I definitely will come and see you.
Please, yeah. And in fact, you will be excited to see that we have some ongoing projects with some of the cities which are considered to be non-attainment, like Tirchi, then Madurai, now Thoothukudi, and then Chennai itself. So we have exciting opportunities for share some of your experience.
Sure. Yeah, I'd love to collaborate.
Thank you. Over to you, Dr. Madhusudan.
Sir, after photo session or now we will?
Yes. Maybe we can also ask. Could you all please, start your camera, Professor Modak? If it is okay, just quickly start with camera and then we'll take one picture.
And the sharing can be stopped, sir.
Okay.
It's okay. It's sharing.
Okay, I'm going to stop sharing. Okay.
Please.
I request everyone to open their camera so that we can catch the smiling face.
The camera is open.
Lakshmi, okay. Yeah, good. Who's taking the picture?
Nobody, I think.
I have taken.
Okay. Yeah, Swaroop, you are taken.
Thank you.
Thank you, Swaroop.
And I look forward to visiting IIT Madras. Obviously, I went to school there, so I have a lot of fond memories about IIT Madras. So,
yeah, please.
Yeah, I definitely want to visit. And but one of these days, we have to conduct a course in micrometeorology. I've been telling Shiva this. We have to do it.
Yeah, Professor Venkat, definitely, surely we will plan to conduct this micrometeorology course. I'll work on that one.
Okay.
Okay, Dr. Madhusudan, please. Propose open.
Good morning, everyone. Holy greetings from SIPA Network. Today was the 18th Air Quality Management Lecture Series, and we are grateful to Professor Akula Venkatraman for delivering the 18th Air Quality Lecture Series. The lecture was basically on the development of dispersion models for air quality management. He explained how models are used in air quality management, its features, steps involved, and also explained it through 2 case studies. The professor started his talk explaining the genesis of the models and explain it in details about the source-receptor relationships, interpolate between the observations, permit the new sources, and the steps involved in developing a model and issues related to the regulatory model and how difficult it is to be made available for the regulatory approval. He explained the preparatory part of the air mode and how the issues were sorted out, and different variables in the air mode was further discussed and explained. The chronology of the air mode development was quite interesting for the students as well as the technocrats. We were very much glad to see how the air mode was developed, and we are grateful to you for the association and completing it, sir. The modeling the impact of highways, the case study was quite informative, and he explained with the data and graphics how a comparative evaluation of models were done and accepted was explained very well. The impact of barriers, both as mitigation for air pollution and noise pollution, were explained in details. In the concluding remarks, the significance of collaborative approach, interaction, resources to develop the model was explained very well. On behalf of SIPA Network, IITM, we thank Professor Akula Venkatraman. Professor was is always kind enough to attend and participate in all our programs. Earlier also, about 3 or 4 times, Professor was part of our SIPA Network programs. And this discussion was very fruitful for the researchers, and it brought out very good questions. Both researchers, technocrats, academicians like Professor Modak, S.K. Gupta, Professor Karichat asked many questions, and Professor has explained it very well. I take this opportunity to thank all the students, the regulatory partners, the steering committee partners of SIPA for attending the 18th monthly lecture series. I also thank the team behind the SIPA network, Dr. Suvarna, Swaroop, and Lakshmi. And I also thank Professor Shiva, our inspiration, the mentor for the SIPA network. So once again, greetings, holy greetings from SIPA network. Thank you everyone.
Thank you very much for everything. And Shiva, Dr. Madhusudan, Dr. Modak, appreciate the opportunity to talk to you.
Thank you. Thank you so much, Professor.
Thank you all. Happy Holi to all of you. And good night, Professor Venki. I hope you had your dinner.
Oh, long ago.
Okay. Yeah.
Thank
Happy
you.
Holi, Professor Modak. Yeah, thank you.
Now for my drink.
Okay. Yeah. Bye-bye.
Thank you.